Hi everyone. Today I'll be teaching computational complexity, the P, NP, and the MP complete saga. In this lecture, we'll be discussing about algorithms, on how algorithm works, the computational complexity, the different problems, on how time and verifying a solution plays different roles, and how you can eventually earn $1 million if you establish a particular hypothesis. So this lecture is going to be pretty interesting, and let's get started. Before we get into all the technical jargon, let's play an easy game or a simple game. Now you have to play this game in pairs. I've given you nine numbers, numbered 1 to 9. You have to select one number after the other such that the total of the numbers should be 15, and you have to reach 15 before your opponent. So the basic intuition of the game will be to reach to 15 first, and in the process block the opponent from reaching 15 first. Pretty easy game, right? You select three numbers such that you reach 15, and then you strategize to stop your opponent from reaching 15. Pretty basic, pretty easy game. Now let me change the arrangement of the letters a bit and make it somewhat similar to this. Now this is a beautiful twist to the same game. You have to do the same thing, but when now you see, when you select, you start to see a certain pattern. You see the first row has 2, 7 and 6. Add it. The total is 15. Let's say the diagonal. It has 6, 4 and 5. Sum is 15. The other diagonal, 8 to 5. The sum is again 15. If you observe closely, every row has a sum of 15. If you observe closely, every row has a sum of 15. Every column has a sum of 15. Every diagonal, that is, adds up to 15. So the whole game changes to you making a diagonal, a row, or a column first before your opponent. Now, this is a game that you have played before I started this. This is a game that you have been playing for a long time, and you have a subconscious strategy on how to win this game. Do you remember a game where you had to make a row or a column or a diagonal with a particular character? Does that sound familiar? It is the classic game of tic-tac-toe. So if observe closely, the solution to all the three problems that I mentioned was somewhat similar. If you observe closely, the solution to all the three problems is somewhat similar. If two or more problems can be reduced to the same problem, they can be solved by the same strategy. And this strategy is called algorithm. So to define, an algorithm is a set of process or rules to be followed in calculations or other problem solving operations, especially by a computer. They are series of steps designed optimally so that a computer can complete a given specific task. Now coming to the problems, in computer science, there are a lot of different problems. So coming to computer science, there are a lot of different problems and scientists have been researching on it. A part of problems is computational complexity, on how complex the problem is, on how difficult it is to come to a solution or to design an optimal algorithm for it, and how difficult it is to verify the given solution that is obtained from an algorithm. On basis of that, we broadly classify problems into two parts, that is P, polynomial problems, and NP, non-deterministic polynomial problems. Now to start with P problems or the polynomial problems are the problems which computer can solve in a reasonable amount of time. And if given the solution, you can figure out if the solution is correct or not. Now some basic examples for this would be multiplying two numbers, adding two numbers, dividing two numbers. sorting the elements of an array, swapping two numbers. These are all polynomial problems. These problems can be solved in polynomial time, or an algorithm can be designed to solve these type of problems in polynomial time. And if you are given a solution, you can also verify the following problems in polynomial time. These are some basic P problems. Now coming to NP problems, or non-deterministic polynomial problems, these are the set of problems where the solution is calculated in exponential time. But if you're given the solution, it takes polynomial time to verify it. That simply means that it is difficult to design an algorithm to solve the problem. But if I give you a certain solution or not, you can check and tell me if the solution is correct or not. Some examples of NP problems are traveling salesman, SAT problem, and graph coloring problem. Now, to quantify things or to put things into perspective, if you have 100 steps, and if the problem is of polynomial complexity, and the degree of the polynomial is cube, it approximately takes 3 hours for the computer to completely process. Similarly, if for the same number of input, if it's an exponential, if it's order of exponential, it takes approximately 300 quintillion years for a computer to solve it. And now that's a lot of time. Now, how do I design an algorithm to solve such problems? For this, we define a set of problems called NP-complete problems. Now, NP-complete problems are a class of computational problems where no efficient solution or algorithm has been found. As we discussed earlier, the traveling salesman, the satisfiability problem, the graph covering problems, and a lot of problems. Even strategizing battleships, Super Mario Brothers, optimizing the best placement of Super Mario Brothers, battleships, Sudoku are all NP problems. They and they are somewhat related. Now, to establish this fact, let me quiz you. Do you think solving a Sudoku is remotely related to optimally planning a trip? Do you think you finding a way to optimally solve a Rubik's Cube will help you set a high score in Candy Crush? Or is your strategy of playing Super Mario Brothers, the OG version, I see, the OG version, somewhat related to solving potential problems like cancer? Is that something that is related? Now, these two things appear to be completely different. But as we move on in the lecture, you'll find that these two things are somewhat related. And if you find a solution to one of them, you'll create a revolution. To move further, let's focus on a particular problem. Let's say I have a group of friends where some friends get along and some friends don't. And of course, it's your birthday and you're throwing a party. Now, the goal is to invite at least three persons and not invite people who have a problem with each other. So that bad, there's no bad blood in the party. So everyone enjoys and there's no clash happenings in the party. Pretty obvious, right? And you have to design an algorithm for that. As a computer scientist, your basic intuition should be to assign each each of your friend as a node, and if they go well with each other, connect them through edges. If not, do not connect them with edges. And then you find a subgraph such that you invite that particular subgraph such that there are no conflicts in it. Let's visualize that. So let's suppose that you have four friends A, B, C, D. Let's name them Alice, Bob, Charlie, and Dennis. Bob and Dennis don't get along with each other. So we haven't connected them. the others get along with each other and the connections are pretty evident. So in this particular case, you have to invite at least three people and you do not have to invite people who do not go well with each other. So in this instance, we'll go for Alice, Bob, and Charlie, or Alice, Dennis, and Charlie. This is selecting a particular subgraph among the given graph. As we discussed earlier, we select a subgraph and invite that particular bunch of people. Now, finding a subgraph among such graph is called clique. Finding a clique is an NP problem. It's very difficult to find that. We'll see this as we go further. But given a particular subgraph, I can easily tell you, or you can easily tell me if the particular solution is viable or if the particular solution doable or not. So let's design an algorithm, a brute force algorithm to select how nodes work, to select how how we go about this problem just on the basic instincts. So we start, suppose there are n people and we have to select a group of 5. So every time we select a group of 5, we check if they are all connected by an edge or not. If they are connected, you have got a click of 5, you exit. If not, then you check if all the groups that have 5 connection have been visited or not. If not, you repeat the algorithm. If all the clicks have been visited and you do not find anything, you exit and say there's no combination possible. This is the basic instinct on how you solve such problems, but there's a very big underlying problem with this. The steps to compute to the input is very huge. So for say 20 nodes, you have to find a subgraph that has 12 nodes in it such that each node is connected to every other node. That requires approximately 126,000 steps. Double the nodes and double the number of nodes you want in a network, the amount increases exponentially. So we somewhat found a solution to an NP problem, but the solution is not scalable. So the problem is not solved completely. It only works for a small amount of people, and such solutions are not established or are not called complete solutions. Now, this is where non-deterministic polynomial time comes into place. A non-deterministic algorithm is an algorithm which, even for the same input, can exhibit different behaviors on different runs as opposed to a deterministic algorithm. Now, this is how you define randomness, right? For the same input, it's different. So how does that work? It is like guessing. So let's factor that thing into the algorithm and optimize it. In theory, it is said that all the computations run parallelly and it gives out the first best output it found. That is why they're different every time. It repeats the same process, but then it takes significantly less amount of time to calculate that. Now this is an NP-complete problem. Non-deterministic polynomial algorithm automatically gives out the best cycle from the given network of the desired nodes. For instance, it will scan through all the nodes, all the networks that have 5 nodes in it, and give out the best thing. And this will reduce the overall time that is taken by the algorithm to compute the solution. Now it continues and to check parallelly. There's a very famous lecture of Eric Damon. He's an MIT professor, a distinguished celebrity, a distinguished computer scientist who currently teaches at MIT. He says that deterministic polynomial algorithm is like engineering luck. It is like using your luck to find the best solution. Now, it is said that it computes all possibilities parallelly and gives you the best or the first answer that it gets. Now, this sounds a bit problematic or sounds a bit different on how can you factor in different outputs on a similar input. How is this not randomly choosing the inputs? Or what sense does it, how does that make sense? Why even believe in such non-deterministic algorithms in the first place? So there was a purpose for which non-deterministic algorithms were established. Now the whole purpose is not for real computation. Such random outputs cannot be factored in to get real answers or to put up real computations. These were used as tools to understand the problem better. We'll see eventually how these types of algorithms helped us to cluster problems. Scientists were working on a lot of different variety of problems, and when a theory for non-deterministic algorithm was established, they could cluster all the problems into a single pool. Now, non-deterministic algorithms all combine to say that the crux of all the NP-complete problems was to establish a guess. The guessing of the optimal solution was the hardest part. Every other thing was still quantifiable, but the guessing was the hardest part. Now, how any of this was relevant? Now, solving a non-deterministic Turing machine is the closest that we have solved to NP problems. A very old computer scientist established a connection between a SAT formula and a non-deterministic Turing machine. And this led to a discovery that a set of problems in NP problems called NP complete problems were somewhat related. The whole idea behind the problems was somewhere the same. And the hardest part among these problems was guessing. So if you could solve one problem, you could transpose it and solve the other problems as well. And this is where it gets interesting. If any of the NP problems that are solved, every other problem in that set eventually gets solved. Now, this is a tree of reductions where you this was a paper that was published in 1972 by Karl Karp. You can see how he reduced every other known NP problem then to the same problem. So if you follow the route, it all traces back to one complete problem. Now, till now, we have established two facts. All the NP-complete problems have a common connection, and if we solve any of the problem that has a polynomial complexity, all the NP problems, and if we can solve the NP-complete problem or find an algorithm to solve it in polynomial complexity, we can solve an NP problem. This leads to a very interesting thing. Now, this is the complete Venn diagram of it. For this, when P is not equal to NP, this is something we'll discuss further. For now, this is a Venn diagram where NP complete problems are a subset of NP problems, and P problems are also a set of NP problems. So P problems can be solved in complexity of less than exponential, that is obviously polynomial. And NP complete solution are problems that are somewhat related but are also an NP problem. Now, this gives rise to a very interesting scenario that has been intriguing computer scientists for a longest time. And that's $1 million question. Is P is equal to NP? Are the solutions which are easy to verify and hard to solve also easy to solve? That's $1 million question. This problem has been in pop culture a lot. So if you see Simpsons, in one of the episodes of Simpsons, you see David X. Cohen. He's a pretty renowned writer and a fellow computer scientist from UCB. He was writers on one of the shows of Simpsons, and he's one of the believers of the hypothesis that polynomial and non-deterministic polynomial problems are somewhat same. And Jeff Westbrook, his counterpart writer on Simpsons and a writer on Futurama, which David X. Cohen produced, still believes that P and NP are two separate problems and they're not equal, they're not the same. Now, here's the real question. Are questions that are verified in polynomial time solvable in polynomial time? This is somewhat confusing, but if you pay close attention to it, I think this is quantifiable. So, the polynomial problems are the problems which are easy to solve and easy to verify. Non-deterministic polynomial problems are the problems which are difficult to solve but easy to verify. But if if this condition equates, that means are there some problems or can we devise an algorithm to solve any one of the NP problem? We have already established that NP complete problems are somewhat related and new problems are added to the set daily. If we establish a solution for any one of the NP problems, we solve it in algorithm time. And if we do that, we eventually prove that P is equal to NP. That NP problems can be solved in can be solved in polynomial time. So why is this so important? Why is this theory so chased, or why does this hold so much importance? Because if P were equal to P, you could derive to a solution by guessing a solution. Now this sounds a bit counterintuitive or somewhat difficult to understand, but this is very interesting. So, for instance, if you are given a strategy, you can guess if the particular investment strategy is good or not. Similarly, if you can guess, you could also get the optimal strategy. So, in that case, if there is a solution to an NP complete problem, if any of the scientists does prove that P is equal to NP, we the world completely changes. Let's take an example of encryption. If it's easy to decrypt and easy to encrypt, the whole idea of encryption breaks down. If it's easier both the ways, the whole banking system fails. It has applications to music composing, to designing investment strategies, to a lot of stuff. This is somewhat that can lead to a lot of tremendous changes in the society as well, because the whole system collapses, because the whole idea is based on you always striving to get the proper solution. But if it is established that it is very easy to guess the proper solution and to verify the best solution, this is where the whole confusion is. If that is established, everything, as popular music producer John Lennon said, everyone will live in peace and everyone will be happy. That's it. Thank you.